Hello, everyone. I'm Houjun Tang, a computer scientist at Lawrence Berkeley National Laboratory. Today, I will present our paper, Battle of the Defaults, Extracting Performance Characteristics of HDF5 under Production Load. First, I will talk about the I/O stack on the supercomputing systems. So the high-performance computing applications often utilizes the high-level I/O libraries such as HDF5, ADIOS, and PNAT-CDF for their simplicity to handle the I/O requests. These high-level I/O libraries implements the parallel I/O through the I/O middleware such as MPI I/O, which then calls the operating system interface, the POSIX I/O, and interacts with the parallel file systems such as GPFS and Lustre. The parallel file system then forwards the I/O request to the actual I/O hardware. Across this I/O stack, there are various tuning parameters that can be set by the user to improve the parallel I/O performance. For example, on the high-level I/O library, HDF5 allows user to set parameters such as the dataset alignment and metadata cache. And on MPI I/O layer, user can choose to use collective I/O or independent I/O. And parallel file systems such as Lustre allows to set the strap count and strap size. As I mentioned previously, HDF5 and ADIOS, PNAT-CDF are widely used by HPC applications. They provide support for heterogeneous data, cross-platform, and portability. They had the low-level details of MPI level and POSIX I/O and large-scale parallel file systems. The parallel I/O libraries such as HDF5 has a large set of performance tuning parameters that user can set. For example, the HDF5 has its own internal metadata, such as object header, bitrate, and they can be configured to be placed at different places in the HDF5 file. Additionally, the parallel I/O in HDF5 are built on MPI I/O, and then it allows to pass in MPI I/O hints through the HDF5 interface. HDF5 also can be configured with the parallel file system parameters, such as the data layout properties of the HDF5 file. HDF5 provides a set of parameters as a default for all these configurations. However, they are often not optimized for specific systems. The HPC systems such as Summit and Cori, they have very different software and hardware with different performance characteristics. And there exists a performance gap between the default setting and the optimized setting, and the gap can be significant. So in this work, we propose to identify an optimal set of parameters through a benchmarking methods. Our approach includes collecting a large set of repeated benchmarking results with various configurations. We have done the benchmarking on 2 production supercomputers, Summit and Cori. We use IOR, which is a popular I/O benchmark, and we configure it with 3,328 different I/O configurations to represent a broad range of I/O patterns. We then measure the performance with these patterns using POSIX I/O, MPI I/O, and HDF5. We have repeated each set of the experiment for at least 100 times to avoid the system noise. With these many results, we perform our analysis to identify a set of parameters that consistently provide good performance in the benchmarking results. Through our analysis, we have found that HDF5 alignment setting and metadata management are crucial to the overall I/O performance, and that performance difference can be up to 10x against the default setting. This large performance gap mainly comes from the HDF5 file layout and its interaction with the file system. And next, we will go into the details and explain how the HDF5 interacts with the file system. So first, we look at the HDF5 parallel writes. So an HDF5 file consists of various parts. First, HDF5 file has its own internal metadata called superblock. And then after the superblock, there are descriptive metadata that stores the location of the user data that are scattered across the file, and that the descriptive metadata by default can be interleaved with the user's data in the file. And the size of the descriptive metadata is usually very small compared with the user data. For HDFL parallel writes, the HDFL library first selects one rank, usually rank 0, to write a super block, and then having a subset of the ranks to write the descriptive metadata before each actual user data writes. And as a result, the descriptive metadata is often scattered and interleaved with the user data. And the performance may be not ideal in many file systems. Next, we look at the parallel read. So as we have seen previously with the write, that the descriptive metadata and the user data are interleaved. When reading this data back, the HDFL IO library first must have one rank to read the super block and then broadcast it to other blocks, and then having each the rank to read the descriptive metadata so they know where to find the user data that has been requested by the application. It then reads the user's data and return to the user. Next, we see how a file is distributed across the storage devices. So different parallel file systems have different policies. For example, on the left, we have the GPFS striping policy, where GPFS defines its block size as a fixed size, and it then separates the file into a number of blocks and distributed those blocks into the storage devices in round-robin fashion. On the right side of this slide, we have the Lustre striping policy. Lustre provides some flexibility that allows the user to choose the stripe size and the number of stripes. They can also choose the storage devices to put the data in there. Next, we will talk about our benchmarking efforts on the production supercomputers. Specifically, we have done our experiments on Summit and Cori. We have measured the POSIX-IO, MPI-IO, and HDF5 performance as they are executed in the same batch jobs in the computer systems. We have varied a number of parameters for IOR, HDF5, and parallel file system. For example, we have varied the number of total MPI processes, the number of compute nodes, the number of processes per node, the individual IO sizes, the number of IO operations, the HDF5 alignment setting, and this metadata configuration. And for MPI-IO, we choose to use collective IO and also independent IO. And on the file system with Lustre, we set the stripe count and stripe size. Now let's look at the results. First, let's look at the impact of HDFL alignment on the write performance. So we have plotted the CDF of the write time for different configurations. We have write sizes, small write sizes of 16 kilobytes to 215 kilobytes and then to 1 gigabytes. We compared the performance and found that the default alignment setting delivers poor performance as we increase the total write size. And also due to the misalignment of the data writes and the file system blocks of file system sizes, the POSIX-IO and MPI-IO sometimes also performs poorly. Next, we look at the HDFL metadata impacts on both the write and read performance. So through our experiments, we have compared the independent IO against the collective IO, and also comparing the when grouping the metadata at the start of the file against the scattered metadata across the file, which is the default. And also we comparing when flushing the metadata at file close time against the default, that is flushing the metadata during the IO time. And we have found that for both metadata read and write, using collective I/O can improve the performance significantly. So it's placing all the metadata at the start of the file and flushing the metadata at the file close time. So with the previous experiments, we identified a set of tuned parameters that we then use to verify it across more variety of I/O access. So here we have run the experiments on Summit with various I/O access patterns and I/O sizes. So we have found that our tuned parameters are able to achieve better performance compared with the default settings in most of the cases. And next is the results on Cori. On Cori, since it uses a raster file system, it has the additional configuration to set the strap count and strap size. And we have compared with our tuned parameters against the recommendations provided by the raster system administrators. So we also found that on Cori, with our tuned parameters, we are able to achieve mostly better performance against the default setting in the majority of the cases. We further evaluate the real application codes with our tuned parameters to prove its effectiveness. We here have shown 4 different applications. WPIO and BDCAS-IO are IO kernels from the WPIC code, which is the plasma physics that simulates kinetic plasma particles, and the BDCAS-IO reads the data of the WPIC data and then performs a parallel clustering algorithm. WPIO is writing the data to a single file with 8 variables and 256 megabytes per process per time step, while BDCAS reads the file and with 8 variables and also each process with 256 megabytes. Next, we have 2 AMR-EX applications, which are adaptive mesh refinement applications. And the one is called NIX, which is an adaptive mesh cosmological simulation code that solves the equation of compressible hydrodynamics flow. It writes 1 file for each time step with 6 variables and a single refinement level. It also has a rich set of simulation metadata. And in total, it produces 385 gigabytes per time step. The other AMR-EX application is called Castro. It uses adaptive mesh compressible radiation MHD hydrodynamics code for astrophysical flows. It is also writing 1 file for each time step with 6 variables and has 3 refinement levels. And it also comes with rich simulation metadata. And in total, it writes 559 gigabytes per time step. Now we show the results performed on both Summit and Cori with 512 nodes. So on Summit, we see that with WPIC-IO, the tuned configuration achieves the best speedup with up to 12x due to the WPIC-IO pattern, where each process writes contiguous data in large chunks. And with the AMR-EX application, we still do observe a significant speed up with 1.1x to 1.4x on Summit. And on Cori, we do see similar trend where the best performance gain comes from the WPIC-IO, where we observe the 7x performance improvements. And with the AMR-EX, we see up to 4x performance improvements with the single level NIX configuration and 2.7x with the multi-level Castro configuration. In conclusion, we have done a benchmarking analysis with a large set of controlled experiments to profile the I/O behaviors under production loads. We have identified a set of tuned parameters and built them as the default in HDF5 library, and we have demonstrated that these parameters are able to achieve up to 12x performance improvements over various I/O patterns on multiple high-performance computing systems. Our general recommendation is to match the HDF5 alignment size with the file system. For example, it should be set to 60 megabytes for the Summit GPFS system. And it is also recommended to group the HDF5 metadata at the beginning of the file instead of having them scattered across the file with the default configuration. And then it is also recommended to use collective metadata operations instead of independent. Our solution has been adopted by the Oak Ridge Summit supercomputer for production use. We already have 2 modules available to be loaded by the user and to utilize our work. Next, we plan to extend our work towards building automatic and runtime I/O tuner in generic I/O libraries across supercomputers and large-scale parallel file systems. So that concludes my talk today.